All right, welcome to IA201 Motors Controls. Today we are talking about Chapter 8 in the book. In Chapter 8, we continue the review of electromechanical relays. Now, we did hit on solenoids, which is the mechanism that drives relays, mostly, and we hit on contactors already that are a little bit later in this book that we already looked at because we're using contactors. So relays are really something that is more common, especially in smaller circuits. They're really important to understand because they combine solenoids with contacts, and they're used in hundreds and hundreds of different kind of machines and applications. There was a whole concept of relay logic before we had PLCs that allowed me to turn on and off circuits and have logic built into the circuits based on the relays. So I could create logic with relays, and we still have them out there, and we still sometimes have to repair them. So right here on page 189, we start in chapter 8. Section 8-1 talks about electromechanical relays, which is your typical relay. So a relay generically is a device that controls one circuit by opening and closing contacts in another circuit. So that's how they define an electromechanical relay, right? And from a very, very simplistic standpoint, if I look at the symbols, and we're going to get into that later on, there's two sets of symbols associated with the relay. And I'm going to put a little dotted line in here because a dotted line, it means they're separated, right? One set of symbols is usually looks like that. You've got sort of a plus or a minus, and once you charge up that little circle, that's the solenoid, right? By charging up that solenoid, you cause that relay to open and close. But in that same physical device, in the same little relay, I also have other symbols that might look like this, or like this. Okay, so they would imply that when I charge this up, that contact closes or the switch closes. Sometimes I have symbols that show two sets of contacts. So that implies that if I wire up to these 2 points, I get a normally closed switch. And if I wire up to these 2 points, I get a normally open switch. So the same set of contacts, that same pole, can be used either normally open or normally closed. And there's a specific term for that we're going to dive into. Typically, contactors will always be normally open, and you'll see them with just a simple open symbol there, normally open contacts. So it's a very important thing about a relay as two separate devices hooked together by magnetism. One is a coil and one is a set of contacts. All right. We also have other kinds of relays out there. A typical electromechanical relay is the one with a coil. We also have something called solid state relays, which don't use solenoids at all. They use they basically use a special kind of a chip to open and close that circuit. Solid state relays are actually becoming cheaper and more available. So you're going to see more and more devices that use these heavy duty chips to turn on and off power. And we'll dive into them a little bit later in this course. This particular chapter is almost completely about the electromechanical relays. On page 190, section 8-2, it goes into different kinds of relays. You've got general purpose relays, which are like this one or this one, or all sorts of other ones out there. They are generally lower current, less than 15 amps is typical. They are generally, they can be wired up to a whole range of different voltages to energize the coil. They basically, they have a general purpose. So let's go into some of the funky terms, which are really important. on the bottom of page 191 are some key terms that are critical. Single pole double throw, double pole double throw, and 3-pole double throw contacts. All right. Those are your 3 common terms. So the pole itself is the number of completely isolated circuits that a relay can switch, right? Number of completely isolated circuits. So in this relay, I've got one set of circuits on one side of the coil. You can see it here. Now, if I flip this over, we can see that on the other side of the coil, I've got another set of circuits completely isolated from each other. Each one of them has got a separate wire that leads up from the base, going to that little reed contact that flips back and forth. Each one of them has a separately isolated contact points on opposite sides of this particular cube. So this particular relay has got 2 poles, one on each side of the relay, completely isolated from each other. You can see there's even a little air space in the middle here between those 2 copper contacts, so that these are isolated physically as well as electrically, so that when one throws, the voltages running through one won't affect the voltages running through the other one. So they are the poles. They are the number of completely isolated circuits that a relay can switch. So I will highlight that whole definition. It's a very important concept. So a single pole relay, this is not a single pole. It would be if only half of that system was available. Double pole is 2. Triple pole would be 3 sets of contacts. Okay. So this one, who can tell me? Well, we're recording this. This actually has 2 normally open contacts, one on each side of the circuit. So it's a double pole circuit as well. The second concept is the word throw. A throw is the number of closed contact positions per pole. A single throw contact can control only 1 circuit. A double throw contact can control 2 circuits. All right. So let's go through an example of that, because on the top of page 192, it really explains this a little bit better. A double throw here, double throw means that this is your typical relay that looks like this. It's got one flexible piece of copper that is normally closed against one contact and then normally open when compared to the other contact. And that fact that you've got one normally closed and one normally open makes this a double throw. So this particular relay is a double throw relay because I can see 2 contacts in here. One's normally open and one's normally closed. This is the normally closed side and the other side is normally open. That is a double throw. So this is a typical double pole, double throw relay. We also have the concept of breaks. Now, breaks are a little bit less common. Here on bottom page 191, when I talk about a break, the number of separate places on a contactor that open and close an electrical circuit. So if you have a completely separate area within the circuit, like these 2 throws are part of the same circuit. They use the same center reed, that center piece of copper. So it can be either attached to the closed or the open. Now, if you completely break them so that you have 2 entirely separate sets of contacts, as is illustrated in the top of page 192. So I've got 2 entirely separate sets of contacts, as you might have with a contactor. This is called a double pole, double break. So it's entirely separate. These are much, much less common. Typical arrangements for all of these are here. Now, the word single break is generally not, we don't do -SB for most relays. We don't even mention break at all. Simply, if it's a single break, most people just say the word, DPST, and they don't say -SB, right? They don't say that. They only mention the DB, the double break, when you have a double break. Now, the book implies that we do see the term single break, the SB, attached to single break relays, but that is very unusual when you're buying these. So when it comes to single break, it's generally not specified as part of the relay specifications. You only see double break mentioned in specifications when there is a double break. The most common relay out there for small relays is this one right here. Double pole, double throw. That's this one. That's this one. That's this one. They're all the most common relays out there. So you guys all should know what single or double pole are, single or double or triple throw are, and you should know what single or double break is. Recognizing that we don't use the word single break mostly for relays that are single break. Double break relays are a little bit more uncommon. They're more associated with contactors than your typical general purpose relays. Here on the top of page 193 in figure 8.6, we see a very useful little chart where it kind of shows you a cross section of the, they call it a symbol, but it really looks like the cross section of the contacts in the relay. Let's see, you can see this little cross section of the contacts in the relay. And it gives you a form letter, which can then be used for specifications for some devices. The manufacturers use that common code form, but not in all cases, to identify the relay. So this is a very useful thing, especially older contactors and older relays. The book then at the bottom, on the left side of page 193, starts talking about machine control relays. The book calls machine control relays this sort of thing, where you've got a relay or a small contactor that's designed to turn on and off some sort of machine. They're not designed for logic circuits. They're not designed for light duty kind of applications. The book calls them machine control relays. I don't know if that's a really common term in industry, but the book describes them, and they are basically contactors. The book shows the picture of a cross-section of a typical contactor. And in general, you will almost always buy these as contactors. You're not necessarily going to look up machine control relays. So read about them. It talks about contactors, which we already went through. The second classification is reed relays. A reed relay is a special kind of fast operating relay that's inside of a glass tube. It's designed for very specific applications. I built some UV control systems with high voltage relays that were reed style relays. And but for the most part, reed relays are less common now in general use. You almost never find them. And for high speed applications, you're generally not going to buy an expensive reed relay. You're going to use a less costly solid state relay like an SSR. So the reed relays are interesting. It talks about this special class of relay. It shows you a little picture of it. That's useful. Good to know about. Then the thing goes into a magnetic level switch. It's just kind of like a relay, in that you're using a float with a magnetic field in it. So it's basically just a class of a magnetic switch. Magnetic switches are used in a lot of applications. They're used in various security applications. Like you can put a magnet on a door and then put a magnetic switch on that door. You can do them in level applications where you can have different relays built into a switch. You've got door open, door closed. You've got a variety of different applications for these little magnetic level switches. I am not sure, once again, that these are really useful for machine control, but they're mentioned here in the book. The next section is really useful, EMR life. How many times that a magnetic solenoid combination switch is meant to last? And generally they're rated for so many operations. So if you have a high-speed switch, it's going to click open and close a lot during its lifetime. It will fail. Typical magnetic switch operations are designed for millions or tens of millions operation. They're designed to last a long time. However, they do start to fail depending on the conditions you put them in. Arcing is a classic reason why they fail. They have things called arc suppressors that are built into these devices. And then you learn about a snubber and a diode. Diodes are used for DC circuits for arc suppression. A snubber is used for AC circuits. They mention little pictures of that. But in general, contact failure is your number one cause. I'd say probably even with coil failure. Either contact or coil failure are your two causes for contactors to need to be replaced. And sometimes you can clean off your contacts. Like you get in here, you can pull your contacts out and you can clean them, and then you'll have it continue to operate. But don't forget that by abrading these surfaces, you're actually going to cause them to, usually you're not going to get to the same level of polish. You're not going to have quite the same arc suppression. You're not going to have quite the same contact force if you abrade these surfaces. So they will fail again faster the second time around. So if you have to fix a contactor by cleaning these contacts, get in there, clean it, and then order the right contactor to replace it, because you will be needing to replace that before too long. And the book talks about a variety of contact failures, does a good job there. And the contact material is very important. Silver, silver cadmium, gold flash silver, and tungsten. Fine silver has the highest electrical conductivity. However, is subject to sulfidation. Sulfidation, that means you get stuff on there, increases resistance slightly. Silver alloy is less chance of sulfidation. All right, so H-3 has a section in it on troubleshooting. As I've mentioned in previous chapters, I think this is probably one of the most useful pieces of this book. When you do troubleshooting with contactors, one of the most important steps is observation, right? When you energize this, do you see do you see it go down? Do you see that little thing click open and close if you energize this? If it should be energized, you don't see the little magnet energize and the position change of that little reed, or the position change of this set of contacts, then you know you've got one problem. You can often smell a problem with the coil being burnt out. You can often see problems with arcing, a little bit of oxidation, a little burnt kind of appearance around the contacts. So the inspection is probably the single most important thing in there. And the book talks about all the things you might find when you inspect contactors or relays that have failed. You often can manually operate a relay to test that circuit. And I've demonstrated that here in class in both remote and in person. And of course, you've got the use of a multimeter that can be applied to check to see if you've got continuity or no continuity as appropriate in the different parts of the circuit. So this is really useful.